In this video, we want to continue looking at some more examples of Newton's laws, in particular, Newton's second law of motion. In this example, we have a hanging sign. So we have the sign that's hung up by these two ropes here at these two different angles, and we're told a 7.5 kilogram sign is haphazardly hanging, that's the different angles, haphazardly hanging from the ceiling as shown. The angles are 60 degrees and 30 degrees for theta 1 and theta 2 respectively, and we're asked, what is the tension in each rope? In other words, if I've got these two ropes hanging at these different angles, they've got to balance this weight. So how much force is each of these ropes going to be pulling up with? Now, if I change the angles, the amount of force gets distributed differently among the two ropes. So what this question is really asking is, for this specific configuration with theta 1 and theta 2, what is the force in the rope 1? That's the tension in rope 1. What is the tension in the rope 2? So how are we going to do that? We're going to apply Newton's second law, which is to say the sum of the forces equals the mass times the acceleration. Now this is a static situation. Nothing is moving. That means nothing is accelerating. So the acceleration is 0. So instead of saying the sum of the forces equals to ma, we can simply say the sum of the forces is equal to 0. Now, this force, the sum of the forces, is a vector. And what we do when we have angles is we break everything down into x and y components. So you can see that I've already put my xy coordinate system at the point where the ropes are fixed together. And that's where I'm measuring my angles from. And I can simply break these tensions into x and y components and then do the vector sum. So if we look at this, we can see that this vector t2 is going to have x and y components, and I could call that t2x, and I could call this t2y. And we can note that both of these are actually pointing in the positive direction. T2x is pointing in the positive x direction. T2y is pointing in the positive y direction. Now, if I do the same thing for T1, I can say I've got, that would be T1x, and I would have T1y. And we can see here that T1y is pointing in the positive direction, but T1x is actually pointing in the negative direction. So when I do my sum of the forces in the x direction, I need to pay attention to the fact that T1x is actually negative. And so that's what we're going to do. We're going to say if the sum of the forces, vector sum of the forces is equal to 0, the sum of the forces must be equal to 0 in the x direction and in the y direction. And that's what we've written here. We have the sum of the forces in the x direction is T2x minus T1x. That is, I have T2x here, and I also have T1x there. T2x is in the positive direction, T1x is in the negative direction. So when I add the sum of the forces in the x direction, I get T2x, which is positive, plus T1x, which is negative, or simply T2x minus T1x, and we know that's equal to 0. And really we know it's equal to ma, but a is equal to 0, so that is why that doesn't matter. Now if I look at this, I've got T2x is equal to T1x. I simply move the T1x over, and I see that the x components of the tension are equal to one another. And of course we know that because this guy is not accelerating in the x direction. So the forces pulling it to the right must be balanced by the forces pulling it to the left. Now if I look at this guy here, at the triangle here, we can see that T2x is the adjacent side to the angle theta 2, and T2 is the hypotenuse. Similarly, on this side, we can say that's going to be a triangle, and T1x is the adjacent side to the angle theta 1. So these both are going to be the cosine times T2 and times T1. So I can say T2x is T2 cosine of theta 2, T1 x is T1 cosine of theta 1, and I can plug in the values of theta that were given in the problem. And if I solve for T2, I find that it's equal to 0.577 T1. And that comes from summing the forces in the x direction. Now, that doesn't tell us what either of these tensions are because we don't have enough information to determine them both yet. But we do know now that they are related by this formula. What else do we know? How did we get this? We got this by doing the sum of the forces in the x direction. We don't have enough information to solve it completely. What can we do? Well, you probably guessed, we're going to do the sum of the forces in the y direction. And so we have this tension, T2, is pointing up. And the same thing for this tension, T1, the y component is pointing up. So this would be T2y. This would be T1y here. And so both T1y and T2y are pointing up. And then we have the weight, which is pointing down. Now the weight is already 100% pointing in the negative y direction, so we don't have to break it into components. It's already done for us. So if I look at doing the sum of the forces in the y direction, I'm going to have this guy is T2y, and this guy is going to be T1y. And so now we can do the sum of the forces. We can say that the sum of the forces in the y direction, that's the vertical direction, is going to be T2y, which is pointing positively, plus T1y, which is also pointing in the positive direction, and then it's going to be minus mg, because mg, the weight, is pointing in the negative y direction. And so if I do all of that, I can also note that T2y, this is going to be opposite the angle, so that goes with the sine of theta 1. T2y is opposite theta 2, so it's going to go with the sine of theta 2. And so I can plug those in. T2y becomes T2 sine of theta 2. T1y becomes T1 sine of theta 1. I can plug in the 30 degrees and the 60 degrees, and I get that 0.5 T2 plus 0.866 T1 is equal to 73.6 newtons. This mg comes over and becomes positive, and that works out to be 73.6 newtons. Now again, I've got 0.5 T2 plus 0.866 T1. I still can't solve this because I have two unknowns. But because I did the sum of the forces in the x direction, I know that T2 is equal to 0.577 T1, so I can take this guy and plug it in there. So I'll have 0.577 T1 gets plugged into here. That's going to be times 0.5, and then you'll have a term that is involving T1. I'm going to add 0.866 T1 to that and set it equal to 73.6 newtons. When you do that, when you plug that in, you get that 1.15 T1 is equal to 73.6 newtons, and I can easily solve for T1. I get that T1 is 64 newtons. Now we already know that T2 is 0.577 times T1, so I just multiply that by 64 newtons, and that tells me that T2, that's the tension in rope 2, works out to be 37 newtons. T1, that's the tension in rope 1, that's 64 newtons, and our problem is solved. This next example is what's known as the Atwood machine. This is a classic physics example, and it's one of my favorites. So this is a very nice little example, and there's a lot of physics packed into this example. So let's look at some of that. So what is the Atwood machine, first of all? It's basically just a pulley over which you've hung two masses. So I've got these two masses, M2 and M1, and they're connected by a cord, and that cord is draped over this pulley. Now, to make our life simple, we're going to assume that the pulley is fixed in that there's basically no friction with the rope and the pulley, the cord and the pulley. And we're going to also assume that this cord has a negligible mass. The mass of the cord is very small compared to these masses, so I can ignore it. That's going to mean that the tension is uniformly transmitted through the rope. And we also want to have an understanding that the rope is not allowed to stretch. And that's going to be very important for us. It's not a rubber band, it's a cord that doesn't stretch and that has negligible mass. And just FYI, I grabbed this picture off of Wikipedia. This is a illustration of the actual Atwood machine. And you can see you have this pulley here and you have this mass here. It's a little bit more complicated than what we described in the previous slide is just two masses hung over a pulley. But the basic idea is the same. Now, why is this called the Atwood machine? Well, the Atwood machine was named after the guy who built it. His name was George Atwood, and he lived in the 1700s. And he used his device to study the motion with constant acceleration. You know, that's something that we've been talking about. And here's the problem. We know that if I take a mass and I just drop it and let it fall under gravity, it's going to accelerate at 9.8 meters per second squared. And so its velocity is going to get pretty fast pretty quickly. What the Atwood machine does for you is it slows down that acceleration. It gives you a constant acceleration that's much slower than little g. And so it makes it easier to study the motion. The other thing that it lets you do is it actually lets you make very precise determinations of little g, the acceleration due to gravity. So Atwood was actually able to use his machine to measure the acceleration due to gravity. Now you can see the picture here. This is a little bit more complicated than just a pulley with a rope hung over it. His actual design was built to enable him to account for the effects of friction. That's something that we are saying that we're going to ignore. But of course, if you go into a lab and you do an experiment, there's going to be friction there. And so he built his machine to enable him to compensate for that and some other things. But we're going to just look at the basic idea of the pulley with the rope hung over it, and we're going to see how to solve that problem. All right, so we want to understand the directions of everything that's going on in this problem. The first thing that we want to look at is the directions of the forces. And we know that block 1, if we isolate block 1 and consider just block 1 by itself, there's going to be a tension in a rope that's pulling it up, and then there's going to be the weight pulling it down. The weight, of course, we know is mass times the acceleration due to gravity, but I want to point out that I've put it as m1 times little g. That label, that 1, is very important. You have to be very careful how you label things. I have students that get sloppy with how they label things and they really get confused. And so put a little bit of effort and care into how you label things and be very careful about using those labels consistently as you work problems. It's a very important idea. And so similarly, block 2, we have the tension is pulling up and the weight m2g is pulling it down. Now, the thing I have at the top here, understanding the directions, it's not just the directions of the forces that I want you to think about. I want you to think about the direction of how these blocks are moving. Because it's easy to say, okay, block 2 is moving down, that's in the negative direction, and block 1 is moving up, so that's in the positive direction. But that can't be true. Why can't that be true? Well, let's look back at this previous example that we've looked at. We had an example where we had two blocks that were connected by a rope on a flat surface, and we pulled them to the right with some force F, and these blocks slid across the floor together. Here's the thing I want you to think about. If this block M2 moves 2 meters to the right, block M1 has to also move 2 meters to the right, because this rope is not allowed to stretch. they have to move together as one unit. That must be true of the Atwood machine as well. And so if I say this block is going to be moving down 2 meters and this block M1 is moving up 2 meters, we have to consider that as both blocks moving in the same direction, because again, this cord is not allowed to stretch. And so I want you to understand why or how it is that we can consider these two blocks moving in the same direction. That's weird, right? Block 2 is moving down, block 1 is moving up, and we want to say that's two blocks moving in the same direction? How is that possible? Well, let's look here and ignore the math on the left. We'll get to it in a second. I just want you to think about the picture for a second. I've got a coordinate system here, and it's a little weird looking, but I'm going to say this guy's moving up, and I'm going to call that the positive x direction. And so I've got my coordinate system here, and I want to imagine my coordinate system being fixed on my string. And so I'm lining up my coordinate system with the acceleration, and these two guys are going to be, both of these blocks are accelerating together. Well, look at what happens to this coordinate system if it's glued to the string. As the rope goes over the pulley, the coordinate system is going to turn upside down. And so on the right side of the pulley, x is pointing down. On the left side of the pulley, x is pointing up. And so on the left side of the pulley, anything pointing up is pointing in the positive direction. And on the right side of the pulley, anything pointing up is pointing in the negative direction. And so that's how we can consider the fact that both of these have the same motion. We just have to imagine our coordinate system moving over the pulley, and we're just keeping our coordinate system lined up with the way these blocks are accelerating. Okay, so now we can apply Newton's second law to each of these blocks. We can do for M1, we can say the sum of the forces, and really these are all in the x direction. I could have a little x there, but I didn't put it in. But the sum of the forces for block 1 are going to be T, which is in the positive direction. Remember, on the left, everything pointing up is positive. So I'm going to have the sum of the forces on this block are going to be positive T minus M1G. And so I've got T minus M1G, and that's going to be equal to M1 times A. And remember, these subscripts, these are our labels. They're very important. On block 2, I'm going to do the sum of the forces, and I have the T. Now, on the right side of the pulley, things pointing down are positive, so my T is negative, and my M2G is positive. And so for block 2, the forces, the sum of the forces is going to be M2G minus T, and that's going to be equal to M2 times A. Now, I have two equations and two unknowns. I don't know what T is, and I don't know what A is. So how could I solve that? Well, I could solve this equation for T and then plug that into here, and that would eliminate the variable T, which is unknown, and then I could solve for A. But if I look, I've got these two equations. I've got T in this equation. I've got minus T in the other equation. If I simply add these two equations together, I'll get T minus T, and the T will cancel. And so that's how I did it. And so I'm going to have T minus M1G plus M2G minus T. The T's are going to cancel, and on the left-hand side, I end up with M2G minus M1G. That's from adding these together. And then on the right side, I'm going to have M1A plus M2A, and that's what I have here. Now on the left side, I see I can factor out a G because there's a G in each of these terms. And on the right-hand side, I can see that there's an A on each term, so I can factor out an A. And so that gives me M2 minus M1 all times G is equal to M2 plus M1 all times A. If I divide both sides by this term, I can solve for the acceleration, and that tells me that A is going to be M2 minus M1 divided by M2 plus M1 times G. Now, the acceleration is going to be some fraction of g, and the fraction is determined by what two masses you pick. And so if I pick my masses well, I can choose to give me a constant acceleration that is some small fraction of g, a half of g, a third of g, a tenth of g, whatever I want, just by picking the masses that will give me that acceleration. And so I have a nice constant acceleration. And if the acceleration is low, it'll be very easy to measure. I can plug in the how many kilograms the masses are, and I can actually measure little g that way. If I measure the A here, I can solve for little g, and that's how the Atwood's machine can be actually used to solve for the acceleration due to gravity. But that wasn't what this problem was. This problem gave us the masses and said, what's A? And so to find A, all we have to do is plug those masses in. And so when I plug those masses in, I get M2 minus M1. That gives me 0.2 kilograms divided by 0.6 plus 0.4. That gives me 1 kilogram, all times little g, 9.81 meters per second squared. Note the kilograms are going to cancel, and I end up with an acceleration of 1.96 meters per second squared. That's about 5 times less than the actual acceleration due to gravity. Not exactly, but pretty close. And so that's the acceleration of the system. So how do I now find the tension? Well, I take that acceleration and I plug it into either of the two equations. I can pick this one. I know what M1 is. I know what little g is. I now know what A is. It's that 1.96. If I plug that in, that lets me solve for the tension. And so that's what I'm doing here. I've got the tension, T minus M1G is equal to M1A. I can solve for the tension. It's going to be M1G plus M1A. I can factor out the M1 if I want, and then plug the numbers in, and I get that the tension in the cord is 4.71 newtons. And boom, that's the answer to the problem. You've got both the acceleration and you've got the tension in the cord. The next example that I wanted to look at is a frictionless inclined plane. And an inclined plane is basically a hill. It's a flat surface, a plane, that is inclined at some angle theta. And so if I put a block here, and if there's no friction, that block is going to slide down the inclined plane. And so what we want to figure out in this example is, what is the acceleration of the block down the plane? And what is the normal force exerted on the block by the plane? Now, before I get onto this example, I want to point out a couple of things. First of all is my choice of coordinate system. Remember, we've talked about coordinate systems previously. I'm allowed to put my coordinate system anywhere I want. I'm allowed to turn it upside down. I'm allowed to rotate it at some angle. I can do whatever I want with it. I just have to have it there, and that's my point of reference. What I have done here, you can see it right up here, is I've chosen to make my coordinate system tilted so that the x-axis points down the inclined plane and the y-axis points perpendicular to the inclined plane. Why did I do that? Well, if I have a normal XY coordinate system, you can see that as this block slides down, it's going to be moving in both the X and the Y directions. And so I have to keep track of both directions if I use a normal coordinate system. But if I tilt my coordinate system so that the X-axis points down the inclined plane, then all the motion is along the X-axis, and that's less stuff for me to keep track of. Could I do it using a regular old coordinate system? Of course I could. But then I'd have to break everything into X and Y components, and everything just becomes a lot more complicated if I do it that way. So sometimes by being clever in how you tilt your coordinate system or where you put your origin, you can save yourself some work. And so that's what we're doing here. We're tilting our coordinate system to save ourselves a little bit of work. And so what we're going to have to do is we're going to put all of our force vectors on this picture, and we're going to break all of our forces into x and y components, but we're going to do that based on this tilted coordinate system. And when we do that, the angles can be a little bit confusing. And so I wanted to try to explain how the angles work when you're dealing with an inclined plane. And keep in mind, the inclined plane is itself inclined at a particular angle, in this case, the angle theta. So what I've drawn here is two boards that are connected by a hinge. And in this configuration, they're closed and both boards are flat. And I've got a coordinate system, an XY coordinate system that's glued to my board here. And I want to look at what happens to my coordinate system when I raise my top board and let it, separate according to this hinge here. And so what I've done is I've inclined that second board relative to the bottom board some angle theta. And my coordinate system is going to be tilted. And so keep in mind, my x here is pointing straight out from the board. It's going to continue to point straight out from the board. And I've made it green here. And this would be my x-axis, and this would be my y-axis. And what I have here is I want to note, how does my new coordinate system, the green one, the one that's tilted, compare to the old coordinate system, the one that was in blue here? And so I've superimposed my old blue regular coordinate system on top of my new green tilted coordinate system. And what I want you to see is that when the x-axis was flat, the x-axis is now tilted up some angle theta. Because this board has tilted up an angle theta, the x-axis has tilted up the angle theta. Now, what's less obvious, but what has to be true, is that the y-axis must also have tilted down the angle theta. And if I extend my x-axis this way, it would have also tilted over in the bottom half, it would have tilted over that angle theta. Do you guys see that? That's what you need to be able to see, is that when I tilt my coordinate system from the old regular horizontal and vertical axes, my tilted axes are both tilted at the angle theta of the inclined plane. So in this slide, I've just basically summarized the points that I went over in the last slide. And we have, if a block is sliding up or down the inclined plane, the best coordinate system to use is one that's parallel and perpendicular to the plane. In this case, all the motion is going to be in one dimension. And if we were to use a normal XY coordinate system, we'd have to keep track of both of the X and Y components of the motion. Now, in this slide, I have my block, and I've drawn on my block my forces. I have the two forces acting on this block. Now, we already said there's no friction, so the only forces acting on this block are the weight, which is pointing straight down. The weight always points straight down. And the normal force, which is pointing perpendicular to the surface. And so the normal force is going to be pointing along the y direction. It's pointing in that positive y direction. Now the mg, normally the mg points in the negative y direction, but because my coordinate system is tilted, the mg now has x and y components. And so in order to do the sum of the forces in the x and y directions, we're going to have to figure out what are the x and y components of mg, the weight, in this tilted coordinate system. All right, now I have this picture in this slide, and the first thing that you can notice is that this slide is kind of busy. There's a lot of stuff on it. If you try to draw your inclined planes as these tiny little triangles on the page, everything's going to be jumbled up, and you're going to get confused. So one thing I want to suggest to you, that when you're taking notes, when you're working problems, and you're drawing these inclined planes, that you make sure that you draw them big enough so that you can put all the information on it and that you can see everything clearly. It doesn't get jumbled up together. So what do I have here? I've got my original two forces, the green normal force, which is perpendicular to the inclined plane, and I have my blue weight, which is pointing straight down. And now I want to know the x and y components. Here's my x coordinate system and my y axis of my coordinate system. What are the x and y components of the weight? And so if I draw this blue with components along the y-axis and along the x-axis, I can see the y component of mg is going to point this way. The x component of mg is going to point that way. So here is the component of the weight that is perpendicular to the inclined plane. It's along the y-axis, which we know is perpendicular. And here is the x component of the weight, which is pointing down the inclined plane, pointing along the x-axis. What does that mean physically? Physically, what that means is this. This guy, mgy, that's the component of the weight that's pushing the block into the board. It's holding it against the board. It doesn't go flying off in the y direction because the weight is pushing it against the board. And specifically, the y component of the weight is pushing against the board. What do you think the x component of the weight is doing? That's the part of the weight that's making it slide down the inclined plane. So part of the weight is pushing it against the board, and part of the weight that's acting perpendicularly is pulling it down the inclined plane. And so I want you to see, and this is why I did the thing with my hinged board. If my XY axes are tilted over an angle theta, that means my weight has to have an angle theta with the new tilted y-axis. And so if the y-axis were vertical, it would line up with the weight, but it's not. It's tilted over this angle theta. And so this component of the weight in the y direction is adjacent to the angle. That means mgy is going to go with the cosine of the angle. The mg is obviously the hypotenuse of the triangle. mgx, that goes with the sine. That's backwards from the way things usually are. Most of the time, the x-axis goes with the cosine and the y-axis goes with the sine. Why is it reversed here? It's because of the angle that we have. We have the angle that's against the y-axis. And so the way to never screw that up, to always have it correct, is to not memorize x goes with cosine and y goes with sine, but to simply draw your picture and always look at the triangle. Which side is adjacent? That's the one that goes with the cosine. Which side is opposite? That's the one that goes with the sine. And so we can write out the x component of the weight is going to be mg sine of theta, and that's pointing down the inclined plane. We have mgy is the y component of the weight, that's pointing perpendicular to the inclined plane, and that goes as mg cosine of theta. Okay, I'm going to ask you to pause the video in a second. I want you to actually draw this out by hand. I know you have it in your PowerPoint, but I want you to actually stop, get a blank sheet of paper, and draw this picture. Go ahead and do that. Let's pause the video. Okay, so have you paused the video? I really want you to draw this. It's really important that you get the ability to draw this picture because you need to be able to not just draw it, but you need to understand it. And so if there's anything that's confusing about this, please let me know. And I want to point out something else. One time I gave a test and I was lazy and I grabbed a picture of an inclined plane off of the internet and it was reversed from the way that I usually draw them. I don't know why, it's just my habit. I usually draw my inclined planes oriented this way, but the picture that I downloaded off the internet was tilted in the opposite direction. And my students were flabbergasted by this. Oh my God, it's backwards. How the heck could we possibly do anything with that? Well, you should be able to understand how the picture is drawn, and it shouldn't matter if it's reversed or not. You should be able to draw it with your block sitting like that. But if you're really, really confused and you just can't figure this out, you're stressed out on a test or whatever, you could always just redraw it the way that I do it. There's no rule that says you can't redraw a picture in a way that makes more sense to you. And so, don't let things stop you. If something is confusing to you, don't let that shut you down. Find a way to make it work. So in any case, what are we going to do? We're going to apply Newton's second law, and we're going to do it in both the x and y directions. And so first I'm going to sum the forces in the y direction. And so what I have here is I'm going to simply say, okay, Fn is pointing in the positive y direction, so that's positive. The y component of the weight, which we already said was mg cosine of theta, is in the negative y direction. So when I sum up those two forces, those are the only two forces in the y direction. I have positive normal force minus the mg cosine of theta, and that's equal to ma in the y direction. And I've drawn my arrow through my a sub y to tell me that it is 0. How do I know that the acceleration in the y direction is 0? Is it obvious? Look at this block. It's only moving in the x direction. It is not leaping off the plane. It's not flying off in the y direction. It's not crashing through the plane in the negative y direction. It's keeping the same y value. That's why we tilted the coordinate system in the first place, so that this guy would be 0 and our life would be easier. By the way, I found a stray dog wandering around campus, and I have that dog in my office. I'm looking for its owners, but if you hear snorting or weird sounds, that's my dog, or the stray dog that I found here. But in any case, let's get back to the physics problem. I've got the normal force minus mg cosine of theta equals to 0. That lets me solve for the normal force. That's mg cosine of theta. Now remember, I told you there are lots of situations where the normal force is equal to the weight, but there are also lots of situations where the normal force is not equal to the weight. Here's one of those situations where the normal force is not equal to the weight. So how do you know if the normal force is equal to the weight or not? You always just need to do what I did. Just do the sum of the forces in the direction that the normal force is in and solve for the normal force, and that'll tell you what it is. And sometimes it's equal to mg, but sometimes it's equal to something other than mg. But we just do the sum of the forces and we solve for the normal force. And just to remind you, the normal force is balancing the part of the weight that's pushing the block into the plane. And so we already said that this mgy, this mg cosine of theta, that's the part of the weight pushing the block into the inclined plane. That must also be the force of the normal force pushing back. And we see, indeed, that that's what it is. Now we've done the sum of the forces in the y direction. What do you think we're going to do next? Obviously, we're going to do the sum of the forces in the x direction. And there's only this one, this mg, this component of the weight in the x direction, mg sub x. And we noted that it's pointing in the x direction. Now, often what I will do is I will take this vector and I'll scoot it up here and I'll let it be pointing down the inclined plane. Remember, it's just pointing in the x direction, so I'm allowed to move it anywhere that I want. So again, if I have my weight, we know that my weight is going to be pointing straight down, and that's mg. And I know that there's going to be a component, mg cosine of theta, and that's opposite the normal force, and there's my angle theta. Now normally, what I would do is I would draw this guy down here, and that would be the x component, but instead I'm going to scoot it up here, and I'm going to draw it up here parallelogram style. And so this guy in blue here, that would be mg sine of theta, and that's the component of the weight that is pointing in the x direction. And so it's the only force that's pointing in the x direction. Remember, the normal force was pointing in the y direction. There's no friction involved. So the only force that we have in the x direction is this mg sine of theta, and that must be equal to mass times the acceleration in the x direction. And so a sub x, I can cancel both of the m's here, and I solve for a sub x, and I get that it's equal to g times the sine of the angle. And that is the acceleration of the block down the inclined plane. Now, if we look at that, it depends on little g, of course, but it also depends on the sine of the angle. And so we can note that as theta increases from 0 to 90 degrees, sine of theta increases from 0 to 1. And so as the angle gets bigger, the acceleration is also going to get bigger. And I think that our intuition would lead us to suspect that, but the equation is telling us that that's in fact what it is. Now, when we have a formula that we've derived, and here we have this formula for the acceleration of the block down the inclined plane, that is in the x direction, we can test what physicists call limiting cases. That means I've got a formula here that's valid for a wide range of angles from 0 to 90 degrees. I know what the answer should be when theta is equal to 0 degrees, and I know what the answer should be when theta is equal to 90 degrees. And so I can plug those angles in here and see if I get the right answer. I'm testing the formula at its limits. That's why it's called testing a limiting case. And so here I have a sub x is equal to g sine of theta. What is the acceleration if the angle is 0? Now, if the angle is 0, that means the inclined plane is flat. Theta is equal to 0. And the acceleration in the x direction is g times the sine of 0. Well, the sine of 0 is just 0. Does it make sense that if my inclined plane is flat, if it's not actually inclined, that I would get no acceleration? I think that that's what you would have guessed. And so we see that our formula gives the right answer if we plug in an angle of 0. Now, what about if I choose 90 degrees? And so my incline, I've increased the incline of my plane so that it's 90 degrees. The acceleration is going to be g times the sine of 90 degrees. The sine of 90 degrees is 1, so that means the acceleration is g. Now again, this guy's sliding down here, but there's no friction. If it's falling down vertically, what would its acceleration be? It would be little g. And so we can see that the acceleration at 90 degrees and the acceleration at 0 degrees, they give the right answer when we plug them into our formula. And so that's one of the things that gives us at least a bit of confidence that our formula is correct. If I had messed up and I screwed up my trigonometry and I put that my answer was cosine of theta here, these would let me check and make sure that I got it right or didn't get it right, because if this was cosine, I would get the wrong answers. These would be reversed. And so sometimes checking limiting cases, when you know what the answer is at a particular value, you can plug in that value to your formula and just check and make sure that your formula makes sense. Now, that's the last example that I want to cover in this video, but I want to end this with a little bit of general advice, because you're already starting to see that there are lots of different applications to this very simple equation, Newton's second law. We've looked at several different examples that don't look anything like one another. We had the block that was hanging from the ceiling. It wasn't moving at all. We had the Atwood machine with the 2 blocks and the rope and the thing going over a pulley. We had the block sliding down a hill. I mean, there's a lot that's very different from all these different examples. And it can seem like an incredible amount to memorize. You have to memorize all these different examples. And it's like, oh my gosh, it's so much. How could you possibly learn all of this stuff? Well, the problem is that students will often focus on how these examples are all different from one another, rather than focusing on how they're all incredibly similar to one another. What are we doing in all of these examples? We're drawing a picture, and on our picture, we're drawing all of our forces. That's the first thing that we're doing. then we're picking a coordinate system that's appropriate for the picture. And being able to do that comes with a little bit of experience. But even if you pick one, like I talked about with the inclined plane, even if I picked a regular coordinate system, I could still work the problem. It'd just be a little bit harder if I used the regular horizontal, vertical, XY coordinate system. But I could still work the problem. So what are we doing? We're drawing a picture, we're putting our forces on it, we're drawing a coordinate system. Then what we're doing is we're doing the sum of the forces in the x direction and the sum of the forces in the y direction. All of these problems have those steps in common. We draw a picture, we put our forces on the picture, we put our coordinate system, and we break all of our force vectors into x and y components. So as we're looking at all these examples, pay attention to that. That's the 90% overlap. In some examples, the acceleration is 0. In other examples, it's not. In some examples, there are multiple angles and multiple blocks. In some examples, there's one block and one angle. But the approach is the same in every case. And so if you start thinking about these problems as, okay, how are my forces pointing? What kind of coordinate system do I need? And then break your force vectors into x and y components according to your coordinate system. Then it's just the sum of the forces in the x direction equals the mass times the acceleration in the x direction, and ditto for the y direction. And so start thinking about this as you're looking at these examples. It makes them not seem as crazy because they're all so common to one another. Even when they seem radically different, there's a lot that's the same. And if you focus on the things that are the same in each of these problems, it becomes easier to tweak them here and there when there are these little differences. So that's my advice for you as you're working through these examples. Please do pay attention to that.